Hello and welcome to a short video on the reaction turbine apparatus and the reaction turbine experiment. So we have a modular sort of reaction turbine module here that's connected to a base unit here. Now, this base unit will allow us to measure flow rates and forces, pressures and temperatures, that kind of thing. Okay, so there's different modules for this apparatus. Currently I have it hooked up to this reaction turbine module. So what I'll do is I'll run through the main components of the apparatus, and then I'll do a quick run through the procedure for the experiment itself. Okay, so on this reaction turbine module here, the main component of it obviously is the reaction turbine itself. So this unit here contained within a sealed housing. Okay, so the reaction turbine, the way it operates is you have a compressed air supply coming in through this tube here, and compressed air will then run in axially along the axis of the turbine inside here. Okay, so the reaction turbine, you have an axial flow of air coming through as opposed to, say, an impulse turbine where you'd have a tangential flow. This tube here to the right hand side, then this is the outlet or the exhaust from the turbine here. So that comes back over to the base unit over here, and we can measure the airflow, the mass flow rate of the air in grams per second. And that should be the same as the airflow rate coming into the turbine, according to your continuity principle. Okay, so the turbine itself then, it's mounted on a shaft, on bearings, and at the back of the shaft here we have a pulley. Currently that pulley isn't connected to anything, there's no mechanical load on it at the moment, so you can see it's just free running pulley at the back there. Alright, now at the back of that then there's an optical sensor, a tachometer. You can just about make it out in shot there. I'm going to move this around, we'll have a look at the back of it in a moment, but there's an optical sensor on the back there that will measure the speed of this pulley as it rotates around. And we can measure that in RPM and convert that into omega in rads per second. Okay, so as I said, this isn't connected to any kind of a generator or anything, but to simulate the effect of a mechanical load, what we have is this brake band apparatus here. So there's a pulley, I believe it's 28 millimeters diameter or 14 millimeters radius or thereabouts. This pulley mounted on the shaft of the turbine. Running around that pulley then we have this brake band, so this unit here. Okay, so it's a leather band, but there is also some kind of friction material. Not sure how well that comes across on camera there, but there is a friction material in contact with the surface of the pulley itself. Now we can adjust the amount of friction frictional force between that brake band and the pulley by adjusting this lever here, so this arm. Okay, so if I tighten this screw here, this thumb wheel on the right hand side, that lifts up that arm and it places tension on that belt, and that would be the normal force. So that tension multiplied by the coefficient of friction between the brake band material and the pulley, that will apply a torque to the pulley. Okay, so as this pulley rotates around, if you tighten down on this and you lift the arm, that gives you frictional force between the brake band and the pulley itself. Okay, now to measure that force, that frictional force, and therefore also the torque on the pulley. So if you know that force and you know the radius of the pulley, you can work out the torque on the pulley. But to measure that force, what we do is we have that attached to a strain gauge cantilever up here at the top. So as this pulley rotates around and you have a certain amount of tension on that belt, you'll get a certain frictional force between the belt and the pulley, and that will tend to pull down on one side of the belt over here. We can measure that vertical downwards pull on this belt here. If you follow that up, this leather strap is connected to one end of a cantilever beam up at the top here. So just a small little cantilever beam, 50 millimeters long or something like that. But the frictional force here will cause a downwards force on this strap, which will cause a downwards force on the free end of the cantilever beam. So that's going to cause this to bend slightly. And mounted on the top of the cantilever beam, then we have a strain gauge here. So if you apply a downwards force on the end of the cantilever beam, it'll place the top of the beam in tension, and there'll be a tensile strain on that. And this strain gauge here then will measure that strain as a change in resistance in small wires, essentially. But that then is calibrated that we can read off force. So a certain amount of force on this here will cause a tensile strain on the top of the beam, and it would be proportional. So the more force you have, the more tensile strain you have on the strain gauge. That then is calibrated such that we can read off here, if you apply a certain downwards force on the end of the cantilever beam, you can measure that force in newtons on this unit over here. Okay? So the reason for that is what we're going to do, and the basic idea of this experiment is we're going to start the turbine running with zero load on it, just have it running freely. And we can gradually increase the amount of tension on this belt, which means we'll gradually increase the amount of torque that's being applied to this pulley. Okay, so what we want to do is we want to kind of measure the torque speed characteristics and the power characteristics of the turbine itself. Okay, so what I might do is I'll turn the unit around and we'll have a quick look at the back of it, and we'll see some of the major components. Okay, so this is the back of the apparatus here. This is the air inlet that's going out to the inlet to the turbine. There is a thermocouple mounted on that. See, there's a little green and white wire here. There's a thermocouple for measuring the temperature of the air going into the inlet. And you also have another thermocouple down here. If you look, that's measuring the temperature of the air coming out at the outlet. So you can measure the difference in temperature as the air goes from the inlet to the outlet and see how much work or how much energy by that difference in temperature. This is the optical sensor then that I mentioned before. So the optical sensor is emitting light, and then it can measure. We're seeing there the back of the pulley. So as the pulley rotates around, there's one half of that pulley is black and one half of it is silver. So this optical sensor here measures the number of rotations, so the number of rotations per second. Okay, and it converts that. There's a conversion then into RPM. This little copper tube, this little copper tube here, that just blows a little jet of air onto the back of the pulley to keep it free from particles and so on. Okay, so it's, as I said, this is the air, compressed air coming to the inlet. Coming off of that then there's a pressure gauge here, a mechanical pressure gauge and also a digital pressure gauge. And that is this unit here that allows you to record the pressure, the air pressure coming in of that compressed air supply. I think those are the main components of the system. In terms of the measurements then, if we go back to the base unit over here, this unit here measures the force from that cantilever and strain gauge setup. This unit down here will measure the output from the optical sensor, the tachometer, converted into RPM, revolutions per minute. These two wires here, these are the two thermocouples from the inlet 1 and the outlet 2, and they are displayed here on this unit, so you can select between different thermocouples. So the temperature at the inlet at the moment is 18.7 degrees, temperature at the outlet is 19.1 degrees, so they're almost the same at the moment. But as you run the experiment, you'll see a difference in temperature between the inlet and outlet temperatures. Okay, and I believe that's all we're measuring in this experiment. The flow rate as well in grams per second. So as you run the experiment, the air coming from the outlet of the turbine, the exhaust, comes up through here, and it essentially lifts a weight inside this here, depending on the mass flow rate of air. Okay, so that's the apparatus. Now the procedure for the experiment, what I'm going to do, now this can get quite loud, so I'll run through the basic idea of the procedure first. Then I'll run the experiment, but I may need to edit the video to sort of decrease the noise and do a voiceover if possible. But I'll go through the basic procedure for the experiment first of all. So what I'm going to do is I'm going to increase the air pressure coming in the inlet here, and therefore the flow rate, with the pulley free running. So with zero load on it, I'm going to adjust the air pressure to bring this turbine up to maybe, let's say a rotational speed of 20,000 RPM, for example. Okay, so I'll bring it up to 20,000 RPM with zero load on it. And then what I'll do is I'm going to increase the brake band tension here by adjusting this screw and measure off the corresponding values of force from that strain gauge set up there. But I'll increase that force in steps such that it brings the rotational speed of the turbine down from 20,000 down in steps of maybe 2,000 at a time. So 20,000, 18,000, 16,000 RPM, all the way down to zero. And we need to record at each step, we'll need to record what is the force on the brake band, and that'll allow you to work out the torque. What's the speed in RPM, and we can also record the inlet and outlet temperatures as well. Okay, the flow rate should remain constant, but I'll check that at each time as well. Okay, so if I start up the compressed air supply to this, as this thing increases in speed up to, let's say, an initial value of 20,000, it will get quite loud, so you may not be able to hear my explanations. So I may need to, as I say, put in a voiceover or something like that afterwards. Okay, so to increase that pressure, what I'm going to do is just adjust this here, and I'll bring the pressure up. I'm not sure the actual value we'll need for the pressure, but I'll bring the pressure up enough such that the no load speed of the turbine is 20,000 RPM. Okay. And you can see as I increase the pressure, the flow rate here, flow rate is at about a little bit less than 3 grams per second. You can see the rotational speed in RPM is about 8,500 at the moment, 10,000. It's worth noting, I'll just stop the turbine for a second. It's worth noting that this speed value here only updates every few seconds, so it averages out the speed over perhaps 5 seconds or something like that. Okay, so there is a slight lag or a delay between any adjustments that you make and the speed being measured out here. Okay, so I'm going to increase that air pressure again such that that speed of the turbine goes up to approximately 20,000. It's hard to get it exact, but we'll get it close to 20,000 and then record that initial value. So I'll just pause the video for a moment and I'll get that set up and I'll come back to it then. Okay, so I've set the initial pressure I've set the pressure of the compressed air to approximately 30 kilopascals. And the flow rate, the initial flow rate is approximately 3.5 grams per second. So what I'm going to do now is I'm going to adjust the brake band tension such that there's just enough torque to drop the speed of the unit down to 18,000 RPM. Okay, so we can see there that there's a small amount of force on that brake band, about 0.06 newtons, and the speed of the turbine has decreased to 18,000 approximately. If I increase that brake band tension further, now we see that a force of 0.12 newtons, and we have a speed of approximately 16,000 approximately. So with a speed or with a force of about 0.2 newtons, we have a speed of about 14,000 RPM. You can see that the airflow rate isn't changing; it's still at 3.5, and the pressure doesn't change. That pressure is a constant at approximately 30 kilopascals. Okay, I'll increase the force even further now. So we'll go a little bit more. It's a little tricky to balance it exactly, but I think we had it at about 12,000 there a moment ago. So something like that, at about 0.28 newtons, it's a little bit over 12,000, so that's reasonable. So you'd keep increasing the force in steps, and that should keep decreasing the rotational speed. Okay, so a little bit less than 10,000 there. So if you carry on like that, you carry on increasing the as you carry on increasing the force on the brake band, and you therefore increasing the torque on the pulley. As you keep increasing the force on the frictional force here, it keeps increasing the torque on that pulley. And as the force and therefore the torque keeps increasing, the rotational speed will keep decreasing. So I'm just going to bring it all the way down to complete stall now. Okay. So it's almost at 0 RPM there now. So with a force of about 0.5 newtons, it's down to very, very low speed, and it would eventually stop. As we increase that further, it'll eventually stop. So I'm going to turn off the air at that there now. Okay, and I'll release the tension on the pulley then. Okay, so that's more or less the experiment there. I'm not sure how well the audio will come across because it is quite a loud experiment. But the basic idea is that with zero load on the pulley, with zero torque on this pulley, it'll run at a particular speed for a given pressure and a given flow rate. So in this case, approximately 20,000 RPM at zero load. As I increase the tension and therefore the torque on the pulley, the speed reduced to 18,000. If I increase the torque on this pulley a little bit further, the speed dropped down to 16,000, 14,000, 12,000, 10,000, etc. Now at lower speeds it's hard to get it precise, kind of below maybe 8,000 or 6,000 RPM. Even slight adjustments on the this thing here it'll tend to start to stall out at that. So at those pressures. At higher pressures, there's a little bit more power in the turbine, so it's able to stay going. It stalls at a lower speed. So, in terms of that's kind of it in terms of the readings. I'll provide a set of readings for the force in newtons, the rotational speed in RPM, and the temperatures. The flow rate is a constant value there, and it's in this case it was approximately 3.5 grams per second. That was a constant, and the pressure was a constant 30 kilopascals. But what you can graph out is if you create graphs of the torque on the pulley versus the rotational speed of the turbine, you'll see more or less a linear relationship between them, where if you increase the torque, you decrease the speed. Okay. Now the other thing that you can work out for that is you can work out the power of the turbine itself. So if you know the torque in newtons and you know the angular velocity of the turbine in radians per second, so omega for the turbine, then the power of the turbine is torque multiplied by omega. So what you can do is you can create a graph of the power output of the turbine versus omega, and that is not a linear distribution. It's a curve that has a particular maximum point. So there's a particular rotational speed of this turbine where its power output is a maximum. Okay. So if this is running very, very fast, it's running fast because there's very low torque on it, and therefore it's not doing any work. There's no power. It's not doing anything. And also, if at very, very low speeds, it's not moving very fast, the omega value is low, so the power is not very high as well. So there's low power output at very, very high speeds, and there's also low power output at very, very low speeds, but there's a point somewhere in between where the power output from the turbine is a maximum. Okay, and that should appear fairly clearly if you graph it out. Okay, so that's kind of it for the procedure of this. As I say, I'll provide the data for the force on the brake band, and that force multiplied by the radius of the pulley, and it's actually the line of action of that force goes halfway through the brake band. So I believe that the diameter of the pulley, or the radius of the pulley, let's say, is 14 millimeters, but the radius to the line of action of the force is 14.5 millimeters. So that would be to the middle of the brake band. Okay, so if you take that force in newtons, multiply it by the radius, 0.0145 meters, that gives you the torque on the pulley. The torque on that pulley, which would be the torque on the turbine. Okay? So I'll give you the readings for the force in newtons, and from that you can calculate the torque in newton meters. I'll give you readings for the rotational speed of the turbine in RPM and the force here in newtons. And I'll also provide you then with readings for the temperature at the inlet and the temperature at the outlet. 18.2 and I've taken readings for those separately, so I'll provide